always have this little ritual to set it all up, and it's now yep. Alright, so hopefully today we'll manage to finish the variational problems and how do they tie to linear algebra. And then we can look at some review problems, practice for final exam. It's just on the 19th, right, of December, if I remember correctly. Okay. I have a feeling there was something more I was gonna say, but I can't remember. Is there anything? Oh yeah, I was gonna advertise tomorrow. We have a special visitor, a professor from Berkeley, James O'Brien, who is famous for physics-based animation, computer animation. He's gonna be talking about like image forgery, how to detect that. It's gonna be pretty cool. So if you are around,
where is it?
Right here at Wen Chen, okay. Levin 101 at 3 o'clock.
From us Thursday?
Yep.
Yeah.
Alright, so let's finish this. I'm sorry I didn't manage to finish it the last time. Just this 15-minute slots don't work so great for me. So what we were doing, we were giving. So let me just quickly recap. What was it, and where did we end? And then how to finish it off. So this is basically a variational justification for SVD, or like one way how we can arrive to SVD from just solving variational problems. And the variational problem we are solving is like this. We are giving a matrix, m by n real matrix, and we want to find the vectors x and y, which are both unit, and their outer product, that the xyt, approximates A as closely as possible. So this is what we were doing the last time. I started by formulating this objective, right? We realized it doesn't matter what I scale it with and so on. I will gloss over the details now. And I massage this objective until I get to this expression, minus x transpose A times y, where the x and y are the unknowns. Those are the variables we are solving for, the unknown vectors. We know that they must be unit. And so the original problem of minimizing this expression, that's our objective, we wanted to minimize. So this problem is equivalent to maximizing this xtay, because the objective is some constant which doesn't depend on x or y minus this thing, right? So if you want to minimize this, then what we need to do is maximize this. Yep. So we want to maximize x transpose ay, so I will call it a function of x and y, where all these things are vectors, right? Like imagine little arrows there, that they are vectors. Okay, the next thing I pulled out that was Lagrange multipliers. Because Lagrange multipliers tell us how to essentially solve, or how to find the critical points, the potential solutions of this problem by computing the derivative of the objective and the derivative of the constraint function. So derivative, more accurately I should say gradient, or the vector of all partial derivatives. Okay, so that's what we did, and what we end up with were these two systems, or they are like matrix systems. So in theory it's m plus n equations, and what this means is that for y and x, which both still must be unit, this constraint doesn't go anywhere, are you with me? So if y and x should have any chance of being the maximum of this function, if they are the critical points, then they must satisfy these equations. That a times y minus lambda 1 x is 0, and a transpose x minus lambda 2 y is also 0, where lambda 1 and lambda 2 were the Lagrange multipliers. The next thing we realized was that because we can multiply this one by xt from the left, and the other one we can multiply by yt from the left, and this tells us that in fact the lambda 1 and lambda 2 must be the same, if this has to have any chance to be true. So that means that I don't have to distinguish between lambda 1 and lambda 2 anymore. I can just call it lambda. And then if I take these two equations, now it's all about like figuring out what x's and y's will solve the problem, right? We want to find the solution. We want to find the maximum of the function x dAy, which will be the solution to our original problem. Are you following me? So because the, how would I put it? Does it work? Because the lambda is the same, then I can just write that this becomes a times y minus lambda x. I can put the lambda x on the right hand side, right? The same thing with the other equation. So here I get a transpose x equals lambda y. And maybe here we should start going a little slower. So here what I did. Here I expressed the x from the first equation. So I divided by lambda. So I got x equals 1 over lambda ay. And I plug this expression for x into the second equation, right? So I get a transpose ay divided by lambda, that's here, equals lambda y. That's there. Okay? Everybody follows? And what this is, after I multiply it with lambda, we realize that this is, what is that? You can't tell me. What is this equation? We said it the last, yeah, just, so okay, you can do it. That y is the eigenvector of a transpose a, yeah, and the lambda square is the eigenvalue, right? So that's quite interesting, right? Because what we obtain here is that if y is to be the minimizer of this expression, then y needs to be an eigenvector of ATA, which is sort of cool. Of course, we still have the constraint that the length of y is 1, right? But that's fine, it doesn't matter, because eigenvectors, they must be non-zero, and if it's non-zero, I can just divide it by the length to get a vector of length 1, right? So that can be easily satisfied there. Now if I do it the other way around, I can do it the other way around too. So I can express, what can I express? I can express y from the other equation. So let's see. I can do y equals 1 over lambda atx, and then plug this into the first equation, right? So what do I get after I plug it into the first equation? 1 over lambda. Now the order is important here, so it's aatx equals lambda x. Okay, everybody follows this step? Basically, it's like doing the symmetric thing to what I did before. First, before I expressed x from this equation, I substitute it into the second one. Now I express y from this equation and substitute into the first one. And what I get is this. So if I multiply by lambda, I will see this. And again, the length of x, of course, still must be 1. So what is this? That's again the same story, right? So this time x must be an eigenvector of AA transpose corresponding to eigenvalue lambda squared. Right? That must look similar, familiar if you are remembering SVD. How did we derive that? Do you actually do you remember that in terms of SVD of matrix A? What are the vectors x and y? I'm sort of like blending into the recap review sessions here, slowly transitioning over there. So remember, when we are talking about SVD, we are talking about left and right singular vectors, right? And I was saying that they are essentially the eigenvectors of this type of matrices, right? AAT and ATA. Right? With one of them I got the left singular vectors, with the other one I got the right singular vectors, right? So it turns out that x is exactly the left singular vector of A, and y is exactly the right singular vector of A. It's just another interpretation. But I haven't solved the optimization problem yet. Those are just necessary conditions which the maximum has to satisfy. It doesn't say that an x that satisfies these conditions is going to be the maximum. As a matter of fact, there is a bunch of vectors x and y which satisfy these conditions but are not the maximum, right? Remember, what we are doing here, we are computing the maximum of x, t, a, y, such that norm of x is norm of y is 1, right? So why is that? Why is this not sufficient? I mean, this has multiple solutions, right? Clearly not all of them can be the maximum, right? Why does it have multiple solutions? Or I guess I could ask in a different way. Is there a unique solution, unique y and unique x, that would satisfy both of these? So this is y, right? This is x. And I think that for both x and y, we have multiple choices, right? What choices do we have? The lambda is not given to us. The lambda is unknown. It's just a Lagrange multiplier. That's sort of this helper, this auxiliary parameter we have invented to be able to nicely solve the constraint optimization problem. Well, I guess we sort of already said it, right? For example, the x's are the eigenvectors of AAT, but the AAT, how many eigenvectors is it going to have? So let me see. A was m by n, right? Which means that AAT is m by m, right? AAT certainly is symmetric. Is AAT positive definite? You have 50% of getting it right, so. Yes, of course, AAT of course is positive definite, right? That was this calculation. If I take some z and I do this, then I realize that this is just do I do it? Z t a. This whole thing oh, wait a second, sorry. ZTA. Because this is okay, it's like this. ZTA, which is the square norm of ZTA. Yeah, I did it in the wrong order because this, actually no. So let's see, this is ZTA, so this is a row vector, right? And this is a column vector. So this is really just a dot product. So I can write this, I can write ZTA as ATZ, the whole thing transposed, right? So this whole thing becomes ATZ transposed ATZ, which becomes the square norm of ATZ, which obviously is non-negative, right? So maybe AAT is not positive definite, but at least positive semi-definite. Anyway, that's not what we need here. All we need here is that symmetric, right? Because a real symmetric matrix, how many eigenvectors does it have? That's why we are talking about symmetric real matrices. We said that this is the nice case where we have the full set of eigenvectors. There is m linearly independent eigenvectors, right? And every single one of them will have some lambda so those will be different x's, and every x might potentially have a different lambda, but all of them will solve this equation, right? And all of the eigenvectors I can just normalize so that they have length 1, right? So this does not have unique solution at all. This has at least m solutions, and this would have n solutions. Okay, so we need to find the one that really maximizes this, that really is the true maximum. So how do we do that? So remember that I said that this is fxy, this is the function we are maximizing, just that I don't have to write xtay all the time. And the task is to maximize fxy subject to, that's always going to be there. So this is actually equivalent to maximizing fxy the whole thing squared. Again, subject to the same thing. Let's think for a second, why is this equivalent? Why can I be maximizing the square of f instead of f? So the only problem could happen if the maximum was negative, right? Because clearly, if the maximum is positive, then the x squared is a monotonic function there, so it doesn't change the ordering. So it doesn't, if something is maximum, then it's also maximum after I square it, right? If it wasn't negative to begin with, but it can't. The maximum of fxy cannot really be negative, because imagine if there was, if the maximum happened to be negative, that means that xtay, that's what the f is negative, then I could simply take minus x and minus y, right? And I would get this. No, I would just take minus x and the same y, which would be minus xtay, which would be something positive, right? So this clearly cannot be the maximum, because I could produce something that would be bigger than that, and which would be positive. So clearly the maximum has to be positive, so I can as well square it and look for the maximum of the square thing. And remember, what was the f? Or what was the lambda? It was somewhere. Notice that before, from this equation, we derived that the f, aka x transpose ay, that is exactly the lambda, right? So this is equivalent to maximizing our lambda squared. Again, subject to norm x equals norm y equals 1. So to solve this optimization problem, to really maximize this function, that's equivalent to maximizing the lambda squared. And that tells us now how to find the real maximum, how to really find the true optimum of that problem. All we need to do is pick the eigenvalue which has the largest magnitude. Right, so largest eigenvalue lambda squared, because the lambda squared is an eigenvalue of both ATA and AAT, right? There was potentially a lot of different eigenvalues, and if we want to maximize it, we want to pick the largest eigenvalue, lambda squared. And that's the solution. So the solution to this relational problem is, So the solution we obtain by forming the matrices ATA and AAT and finding the eigenvectors which correspond to the largest eigenvalue, normalizing them, and that's the solution. That's it. And the interesting thing is that this way we essentially arrived at the left singular vector and the right singular vector, just from this one experiment. So you could say that this is a different interpretation or variational optimization interpretation of singular vectors, that they are the best fit unit approximation, rank 1 unit approximation of matrix A. By unit, I mean that the x and y must have length 1. Which I found sort of cool, that there is like a different way to arrive to SVD rather than sort of the standard linear algebraic way, like thinking how do I generalize eigenvalues and eigenvectors to a rectangular matrix, right? This was rectangular matrix naturally to begin with, and the left and right singular vectors, they naturally emerge there. Okay. By the way, this is not the best rank 1 approximation, right? Because for a rank 1 approximation, I can still scale it by some coefficient alpha. So a general rank 1 approximation would be A x y transpose, right? And do you know, you should know, I just want to do a little bit of recap already. If I really wanted the optimal rank 1 approximation, what alpha should I pick there? The x and y, they would be the same. The x would be the left singular vector and y would be the right singular vector. And what do you think would be the optimal alpha there? I'm not going to discuss that in detail because we already talked about this. I just want to tell you the answer. Do you understand the difference? I mean, here we were looking for x and y that were unit length, and what is the best approximation, right? Here we also have x and y of unit length, but then we can scale it by some scalar, right? And I'm not going to derive it in this much detail, but from what we discussed before from SVD, you should at least remember the solution, if not be able to derive it, even though we haven't derived that properly. Interestingly, the x and y, they are exactly the same. The x is the left singular vector of A and y is the right singular vector of A. And what must be the alpha? Yeah, the singular value, the largest singular value. Yes, exactly. Right, because that's what we discussed. That's the Eckhart-Young theorem. That's the low rank approximation of a matrix using SVD. So this is just a special case for rank 1 approximation, right? Okay. So that was our optimization problem number 1, and here is optimization problem number 2. In this case, we will not just like rederive SVD. In this case, we will actually use SVD to solve a different problem. And this problem is about finding best fit orthogonal matrix. I think it's also sometimes known as the Procrustes problem. Or you could also call it like closest orthogonal matrix to a given matrix. So the problem is like this. We are given a square matrix A n by n, and the task is to find a matrix R which is orthonormal. So that means that RTR is identity, such that the Frobenius norm of A minus R is minimized. So in other words, we are given an arbitrary real square matrix A, n by n matrix, and we are asking what is the orthogonal or orthonormal matrix, which is as close as possible to A. A, of course, if A already was orthonormal, then the solution is trivial, right? Then just R equals A. But the point is that A can be any matrix, so probably won't be orthonormal. And we wanna find such a matrix R that's closest to A but is orthonormal. This problem will also, the solution of the problem will also lead to something that's called polar decomposition, which, did we discuss polar decomposition? Right now I can't, probably not, right? It comes up a lot in graphics and physics, and probably elsewhere too. Okay, so how do you think we would solve it? So it's again an optimization problem, right? We have a constraint optimization problem. So we are searching the space of orthonormal matrices, and we want to find the one that minimizes this objective, right? So it seems that again would be a good idea to start by manipulating the objective to get it to some simpler form. So as before, instead of minimizing this, we can actually be minimizing the square, right? Because this is a Frobenius norm. This is always non-negative, right? It cannot be a negative number. So if I square it and look for the minimum of the square thing, I must find the same result, the same R. Okay? And now what is this? How do I rewrite this? So I again use the trace formula just like before. So the Frobenius norm squared is A minus R, the trace of A minus R transposed A minus R. Do you remember this? That's what we used this before too. That's the expression of Frobenius norm using trace. Now we can expand this, so we get that this is trace. So I'm just expanding this product. So this is trace of ATA. That's gonna be plus trace of RTR. Now minus trace of what? Of ATR and minus trace of R transpose A. Right? I guess I could have done it slower, that I could have first said that this is A transpose minus R transpose, right? And this is multiplied A minus R, and then trace is a linear operator, so we can just split it into the separate traces, right? So let's look at these terms. So trace ATA clearly does not depend on R, right? That's some constant term. It is sort of, the problem has sort of similar structures before. It's again an optimization problem, right? How about trace RTR? How much is trace RTR? Yes, that's exactly n, right? Because RTR is identity, and the trace of identity is just n. Doesn't matter that it's n, all it matters that it's constant, right? So both the first and the second terms are just constant. So they don't really matter. Even though this it seems this depends on R, it actually doesn't, which is interesting, right? Due to this constraint that RTR is just identity, no matter what exactly R is. Okay? So all that matters is this term here. And this term is actually just one term, right? Because we know that trace of some matrix M is the same as the trace of M transpose. Why is that true? That's trivial, right? If M is square. Yeah, that's trivial because if I'm just summing the diagonals, if I transpose it, the diagonal doesn't move, so I'm just summing the same thing. While it's trivial, it's actually very important because it tells us that this trace of RTA is the same as trace of ATR, right? So this entire thing becomes some constant minus 2 traces of A transpose R. So that means that instead of minimizing the Frobenius norm of A minus R, I can as well be again maximizing the trace of ATR. Let me discard this factor of 2 here as before. Again, subject to the constraint that RTR is identity, that R is an orthonormal matrix. Okay, so far it has sort of similar story as the first problem, but now the solution will be a little bit different. So we want to find an orthonormal matrix R which maximizes this trace for a given fixed matrix A. And the way we can find such an R is by considering the SVD of A. So let's take a look. So we know that any matrix has a single value decomposition, right? A being no exception. So I can definitely write A as U, sigma, and V transpose, right? And this was a square matrix to begin with, so all these matrices are nice and square. And U and V are, actually you tell me. What are U and V and what is sigma? Because this is a single value decomposition, SVD. So here the idea is that here we will use the SVD to find the optimal R. Okay, so what the SVD tells us about the U, sigma, and V. Let's just review that. Those are some of the things you really need to remember, not just for the final, but like for your linear algebra kung fu in general.
They're all n by n?
They are all n by n, yes. All of them are n by n in this case. And what else can we say about them? They are not just any matrices, right? They are very special matrices. That's what the power of SVD really is, right? So which is which?
So sigma is a diagonal matrix.
Correct, sigma is diagonal.
Use the
And U and V. Right. But what are the properties they have? Because that's why we are actually doing the SVD here, right? They are orthonormal, right? Meaning that UTU is the same as VTV is identity, or because they are square, I could also, they are actually square. U's and V's are square even in the general case, right? Even if A was m by n. So here I'm taking the SVD to be able to find this optimal R. So let's see. So okay, let's assume I have established I found a single value decomposition of A. We know it always exists, so there are no problems with that, right? So then what is the trace of A transposed R? So A transpose is just V sigma UT, right? Why did I not transpose the sigma? Because it's diagonal, right? So diagonal is immune to transposition. So this is V sigma U transposed R, right? And then do you still remember this property of the trace, that if I have a trace of A and B, that's the same as trace of B, A, right? So I can apply this property And how do I apply it? I can do this. I can say that this is equal to trace of sigma utrv. So I took this v and I flipped it to the right. Okay. And now watch this. Well, what is interesting here is that we know that the product of orthonormal matrices is an orthonormal matrix, right? I think you had it in some homework or something like that, right? So U is an orthonormal matrix. Of course, U transpose is also an orthonormal matrix. R is also orthonormal matrix. That's my assumption on R. And V is also, that's also from SVD. So this entire thing, UTRV, let's call this matrix M. M is orthonormal. MTM is identity. So I can write this entire thing simply as transpose sigma M. And interestingly, from this, I can reason about what the R must be to maximize this expression. Remember, the task here is maximizing this. So here we are just like manipulating this expression. So what we need to do is maximize the sigma M, where M is an orthonormal matrix, right? So let's take a look. What is this trace sigma M? So sigma was diagonal, right? Sigma looks like this. Sigma is sigma 1, sigma 2, and so on up to some sigma n, right? And if matrix M has elements m11 and so on, m1n, mn1, mnn, can you help me write what the trace is? So first, for what the multiplication by sigma does, it scales every row, column, one of these, right, of M. Doesn't even matter in this case. Because ultimately we are only looking at the diagonal, right? So what is the trace if I want to write it as a sum of the elements of the matrix sigma M? So what would be a trace just of M? Just of course some MII, right? And if there is the sigma, how does that change?
Sigma I.
Yes, exactly. So this is just sum of sigma I MII. Now we can, so this is what we are maximizing, right? And the only thing we can change here is these m's, because the m depends, it has this r here. So essentially the question here is what m's to pick to maximize this expression, right? And here is an interesting fact, or the fact is that if I have an orthonormal matrix M, then all the elements of the matrix in absolute value must be less than or equal than 1, right? Why is that true? Well, that's because if I have a matrix M like this, and I write the individual columns of this matrix Mn, then this empty M means that every column must, so every column is unit, right? That's because it's an orthonormal matrix. But this means that the sum of, so for every j, where j indexes the columns, if I take the elements of the individual M, this like this, if this was, so this was like my M column M1, which has elements M11 to Mn1, right? Here would be column 2, which would have elements M21 to M12 to Mn2, and so on. And the point is that if I take all these coordinates, all the elements, all the components of the vector M and square them, I get 1, right? So that means that clearly every single one of them squared must be less than or equal than 1, right? Because if one of them was greater than 1, then the others couldn't really fix it because all these guys are non-negative, right? Because we don't have any complex numbers there. Those are real numbers. So square of a real number is non-negative, right? So that means that every single one of these, every single component here, after I square it, must be at most 1. So that means the absolute value of Mij is at most 1, and of course the Mij must be also at most 1, right? There's no way, if it was more than 1, then this could never be true. Do you see that? So what does that mean? That means an interesting thing. If I use this fact right here, that means that because all the MIIs also must be at most 1, right? So I can write an upper bound for this. And the upper bound is simply the sum of sigmas, right? Because I know that MII, there's no way in the world that this MII would be greater than 1. So if I put there 1, I can only increase it, right? So if I just sum the sigmas, I could have only increased it. So the solution, so remember, we are still maximizing this expression. We are looking for these m's such that this thing here is as much as it can be. We are maximizing it. And we cannot get above that. This is just like the limit. But interestingly, we can exactly hit this limit, right? From this you can already see what the optimal m's are. Do you see the optimal m's? Yeah. Just pick MII equal 1, right? That means pick M11 be 1 and so on, and M and N be also 1, right? Now, because the matrix must be orthonormal, that means the matrix M, what sort of matrix is it going to be? It's the most simple matrix in the world. It's the identity, right? Because if I put 1s there, then I have no space here whatsoever for anything non-zero, right? Because the columns must have norm 1, right? So the matrix M, which maximizes this expression, is exactly identity. And what was the M matrix? Let's return back here. I said that the M matrix is just a shorthand for U transpose RV, right? So that means that U transpose RV must be identity, right? And I can compute the R from here, right? I just multiply it from the left with U. So I get this, and from the right with V transpose. So this is U V transpose. Now because U and V, they were both orthonormal and square, and those are identities, and I have that R is U V transpose. That's my solution. So this is the answer. What is the optimal orthonormal R that best approximates A? And how do I compute it? I get the SVD. If you look at the whole picture now, all I need to do is compute the SVD, and then just instead of sigma, stick in their identity. Right? Just basically forget about the sigma, and that's my optimal orthonormal approximation. Just sort of interesting. I promised to explain how does it relate to polar decomposition. Polar decomposition you can get from single value decomposition quite easily. So U sigma Vt, so if I have SVD of A being U sigma Vt, what I can do, I can just put here VTV, because VTV is identity, right? It's not changing anything if I just do that, right? So I basically stick in here identity. I can stick in identity wherever I want. Doesn't change anything. And I can write the identity as VTV, right? Because V is an orthonormal matrix. But then the UV transpose, as we just found, is the best fit orthogonal matrix, or orthonormal, sorry, I sometimes confuse them. So this is the R times V sigma V transpose, and this V sigma V transpose can be called S. And the interesting thing about S is what? What is S? S is clearly symmetric and positive semi-definite, right? Sometimes it's called like the stretch factor because it's like pure stretching without any rotation. That's what a symmetric positive semi-definite matrix means. If A was invertible, then I could say it's positive definite, right? The semi-definite only means there that in the sigma there can be some zeros. If there were no zeros, if A was invertible, there are no zero single values, then S would be positive definite. And this is what is called polar decomposition. So polar decomposition takes a matrix and decomposes it into an orthonormal part R, which happens to be the best fit orthonormal matrix, and the rest, where the rest is symmetric positive semi-definite matrix. Now, an interesting variation of this problem is if I say that I don't want just an orthonormal matrix, but I want a rotation, the special orthonormal matrix. What is the difference between the two? You remember that? Between just orthonormal matrix and the rotation. Rotations are a sort of special case of those, right? There are two possibilities for an orthonormal matrix. There are two classes of orthonormal matrices. Some of them are rotations, but some of them are not rotations. Some of them are what? Reflections, exactly. And the way I tell that, I look at the few minutes, I can use them. The way I tell if I have an orthonormal matrix, so RTR equals identity, then I look at the determinant of R, right? And determinant can be either +1 or -1. You should be able to prove that. I will not be repeating that again. You can verify that by yourselves, that it's either +1 or -1. If it's +1, it's a rotation. If it's -1, it's a reflection. So I could consider a version of this problem, which is actually quite important, like in graphics or anywhere where you need to find the best fit rotation. So we are not fine with an arbitrary orthonormal matrix in this case, but we really want a rotation. So we have there the additional assumption that the determinant of R must be +1. We forbid or prohibit the case of determinant of R being -1. So the derivation proceeds as before, except that here, if we end up with the case that the determinant of UV transpose is -1, then we are not done, right? Because that's not allowed. I cannot say that R is UV transpose, because then I would violate this constraint, right? And what I need to do to fix that is to find an M matrix which has determinant -1, because that will then flip this -1 here, and I will get a positive determinant of R. And it turns out that the solution, I don't know if you could guess this. No, I don't have time. No time for any guesswork. The solution is that the M will be a matrix almost like before, but with the last element -1. Right? So this is my, like, let's call it M tilde. Clearly the determinant of M tilde is -1, right? Just multiplying this thing. And the best fit rotation in this case will be U M tilde V transpose. Before we had U identity V transpose, if this happens to have negative determinant, then we need to stick in the matrix that has the last element -1. Why the last? That's because that's the one that corresponds to the smallest singular value. Okay, I will have to end, but that's good because we are done. Any questions to this? All right, so that's basically it. And on Friday we will do some review problems. All right. You have a question? Sorry, can you repeat it? Yes, there are two versions of the problem, right? In the first time I didn't say that R was a rotation. In the first, the thing I really derived, this one, I said that R is just an orthonormal matrix. But then I say another variant of this problem is if I say that I'm more strict and I require R to be also a rotation, right?
So how do you get to determinant of M is equal to -1 from determinant of R is equal to +1?
Oh, because the determinant, so if the problem was if I arrived to the determinant of UVT being -1, right? If I got UVT and the determinant was 1, then I'm done, right? Because then I have a rotation, right? But if UVT, if my R, or I really cannot call it R, right? If determinant UVT is -1, then I cannot say this is R because I want the determinant of R to be 1, right? So I would have a contradiction. The way I can fix it is by using UM tilde V transpose, because if I take the determinant of this will be the same as the determinant of M tilde times the determinant of UVT, right? Determinant of this is -1, determinant of this was also -1, so the determinant of the whole thing is 1. So this is my R. Okay, it's not like complete explanation why exactly this is the optimal M, right? It's a little bit more complicated, but this is the answer, and sort of intuitive. You somehow need to fix the negative determinant. The way you fix it, you just flip the smallest component there. Okay.